So previously, we were looking at this uniform cost search. And then we saw the properties of this UCS in these four terms. And now we will see what is depth first search. You already know what is depth first search in data structures and maybe in algorithms and maybe in some other courses. So that DFS is same here. We know that if we have a tree and if we are going to start from the root node, then what will happen next? So this is now, this green node is now in frontier. I will explain with respect to the algorithm that we have here with respect to frontier and explore set, okay? So, but the execution of DFS is same. So initially, this node is in the frontier. And then it will be popped from the frontier and then it will be expanded. It will be popped and the two new nodes will be generated and added into the frontier. Then what will happen? How DFS will go? What is the picking order of the nodes? Always on the left and the deepest node, huh? Always on the left. The by default order is what? Always on the left and the deepest node. So that's why it is on the left and it will select this B and it is the deepest. And it will pop this node out from the frontier and then it will generate new nodes D and E. And then it will add them into the frontier again, huh? So then what? So now these gray nodes are in the explore set and these green ones are in the frontier. But you can see this selection criteria. This is selected, then this is selected, and then this is selected. This is like DFS that you have studied already. So now from this D, E, and C, which node will be popped? From the left and the deepest node. So this D will be selected, and then the new nodes will be generated and added into the frontier, which is HI. And then from the left, the deepest will be selected, which is H, and it will be matched with the goal no. Then it will move to the I. Then it will move to the I. It is goal no. Then what will happen? It will go back. In the next step, it will go back and then it will select this E. So, or you can say that when I is not a goal, I, E, and C, I is not a goal, then what are the others in the frontier? E and C. So then it will select E, huh? Or you can generally say like that. Okay, E would be selected from the frontier, popped up, and then the new nodes will be generated like that. Now these green new nodes are in the frontier, and these are in the explored set. And now left and the deepest would be selected. J is a node, no. Then you will go to the next, which is K. You will pop another node from the frontier. And then you will check it is a goal, no. If your goal is, for example, according to this tree, if your goal is M or something here, huh? So then what? If K is not, then what? You will pop the next node from the frontier, which will be this one, which is this C1. But you already know that we will go something like that, and what has the next turn, we will select that according to the DFS. So then C will be selected popped up from the frontier. New nodes will be generated, and the left and the deepest will be selected, and then new nodes will be generated, and left deepest. When it is not a goal, then you will select M. It is a goal. If it is a goal, you will go out of the algorithm. So the execution, so the selection of the nodes here in all these trees is exactly like DFS that you have studied in data structure or algorithm. But here we will use frontier and explore set in our algorithm. Nothing else. So here I'm not going to present the DFS algorithm here because it is available in the next version of this DFS. Okay, so we will see that thing there. So we have seen that DFS always expand the deepest node. If the default order is from the left, then it will select the deepest node from the left. And if you change the order, and if you are selecting from the right, not from the left. For example, here B and C, you are not selecting, you are going from the right, huh? And the deepest, then you will go something like that, huh? So anyhow, so DFS always selects the deepest node, which is available in the frontier. So then what? Is this DFS is a complete node? Is this DFS is a complete algorithm? And the answer is no. Why it is not complete? Complete means if solution exists, does our algorithm give us the solution? This is the definition of the complete. So, and we are saying that DFS is not complete. Why? Due to infinite space, due to infinite depth space. The same thing. If you have on the when you are going something like that in this direction, in this deepest direction, when you are going like that, if you have loopy paths here, if you have redundant paths here, if you have infinite space here, when I say loopy, redundant, infinite, it means repeated path, huh? I told you in the beginning of this CLO, okay? What is in the tree search, states are repeated, and if repeated, we will go into the loopy parts. These are called redundant parts, and that is what then your algorithm will go into an infinite state of execution, huh? So that is called infinite state space. So if so this DFS is not complete if we have an infinite depth space, infinite due to repetition. But if you don't have that repetition or infinite depth space, then you can call it complete, like BFS, like blood pressure. That is also the same condition there. And then if it is not complete, then it is not also optimal, huh? Generally. So if it is not complete, then it is not optimal. So the answer optimal means if you have more than one solutions available, does this algorithm provide us the best possible solution from those? The answer is no. It will not provide us the best solution. Let's see that. Suppose, for example, in this tree, if your solution is M, and if this solution also appears here, if solution is existing two times in the tree, huh? I am not, I'm just imagine that this is just a one tree, huh? And one solution is available here, other solution is available here. But when the depth first search will execute, it will reach here first. And when it will reach here first, it will give you the solution and it will go out of the algorithm. Even we know that this is the optimal solution. So that is the reason that we are not saying that DFS is optimal solution, optimal algorithm. No, it is not. It is not an optimal. Then time complexity and space complexity. So now DFS normally go up to the maximum depth of the tree or maximum depth of the state space. So then what? And then, so that's why we are not writing B raised power D, we are writing M. M is what? M is the maximum depth of the state space. M is what? M is the maximum depth of the state space. So, and in the BFS, we were writing here D, depth of the least scarce solution, huh? But here we are in a DFS, and here in DFS, if your solution is here, maybe, but if the tree has the maximum depth here, it will go first into the maximum depth, okay? And then it will come here on this solution. So that's why we are saying that DFS will go up to the maximum depth of the state space. So then order of B raised power M. And this M, which is the depth of the state space, which is the depth of the tree, you can say, can be much larger than the D. D is what? Depth of the least scarce solution. So this M can be much larger, can have a much larger value than this D if your solutions are deep in the tree. Anyhow, let's see. I have already explained this point to you that your solution is maybe here, but this level is much deeper. So your DFS will first go here at this deepest point. It will execute it, and then it will come here. Then it will come here. So that's why, so that is one reason that we are writing that the time complexity, the number of nodes in the frontier would be, what is the maximum? Maximum M, maximum depth. So that's why we are writing B raised power M. And the value of this M, which is the maximum depth of the tree, can be much larger than this V. And suppose if your solution is available on this depth, okay, not here, okay, not here. If your solution is here, available here, and if you will execute BFS, breadth first search, then it will execute like that. First this level, then this level, then it will reach here and it will reach at this solution. This is BFS. But if you will execute DFS, it will go speedily there. Huh? In the first iteration, it will give you that solution, if solution is available there. So the point is, if your solution is available in depth, then DFS will provide you the solution speedily as compared to the BFS, because BFS is executing breadth-wise. It
would be slower if the solution was in depth to the.
Yes, this is the worst case. This is the worst case, okay? This is the worst case, because then your algorithm has to execute each and every node of the tree. Yeah, that is the worst case. But normally, if your solutions are deep, then that's why we are using the word may be. That's why it may be much faster than BFS if your solution is there on the left side. Space is what? Order of B multiplied with M. Because if your solution are here on this first line, then we are saying the branching factor and then multiplied this maximum depth with depth. We are not counting all that stuff. So that's why here we are simply multiplying with M, and it is a linear space. It is a linear space. So all these things are, so this time complexity is similar to BFS except this M. In BFS we have D, here we have M. And in space, the space complexity of BFS is order of B, D. And here we have B multiplied by M. Multiplied, not the exponent, not the power. And the reason is if the solution is here on this branch, then this is the maximum depth, and then you are saying we are multiplying with this m maximum depth. We are not multiplying with that all stuff. Okay. Now, depth limited search or DLS. There is a problem in this depth first search. There is a problem in this depth first search. And what is that problem? That if the state space or if the tree is infinite, then we will not, when I say infinite, that infinity can occur due to repeated states, okay? Due to repeated states, but you are not seeing any infinity here. So that's why it can create a confusion in your mind. But you have to consider that maybe so maybe this, you will have the A again here, huh? This node A. And if A again here, it will be selected and it will be expanded like this again. This tree will be executed again. So anyhow, there is a problem in DFS that if your this depth is infinite and solution is available after that infinite state, okay, then you will not reach at that. For example, if this is the solution and you are repeating A here, huh? And now you are repeating A here. For example, I'm saying just to give you understand, then you will come here and after the A, you will execute this tree again. Then you will come here and after the A, you will execute this tree again. So this is infinity. And you will not reach at this solution. This is the problem in DFS. This was also a problem in BFS when we were studying that, if there is an infinity. So then what? How we can remove it? So the one idea is DLS, depth limited search. One idea is to fix the depth. Your algorithm will not go, when you will fix the depth, what is the meaning? This is depth level 0. This is depth level 1, huh? This is depth level 2. This is depth level 3. So the idea is we will fix the depth. Maybe we will fix the depth, for example, 2. And if when we will fix the depth, then your algorithm will go like that. First here, then here, then here, then it will come here, then here, then here. And it will not go beyond this depth, okay? This is the idea. Okay, this is the idea of introducing a limit in the depth first search. So that's why it is called depth limited search. That's why it is called depth limited search. So this is the algorithm now. We will introduce a limit, something, and here the function is depth limited search. I should have to paste this diagram before, but anyhow, you can see how this is the next one. Yeah. So now what is depth limited search? If the DFS will give us failure due to some infinite state space, then this problem can be corrected by introducing a depth limit L. And then this approach is called depth limited search. Let's see this algorithm first. Here, depth limited search is the name. We are passing some problem into it. And then we are saying, okay, limit. Limit can be 1, limit can be 2, limit can be 3, and so on. And then this algorithm will return solution, failure, or cutoff. Cutoff means boundary. Boundary which is the boundary for the limit. If you have If you have introduced 2, then this is the boundary. This is cutoff. If you have introduced 1, limit is 1, then this is the cutoff. This is the limit, which is 1. Huh? So now, then we are calling recursive depth limited search. We are calling another function which is written below, recursive DLS. And then here in the parameters, we are passing initial state of the problem, and the complete problem means all the things, all the information of the problem. And then we are passing the limit, which is given here. And then this would be called with the initial node, problem, and limit, and it is returning again solution, failure, and cutoff. So where is that picture? Yes, this one. So maybe I will use this picture for the execution of that algorithm. So suppose our limit is what? Our limit is 2, okay? Our limit is 2. And the problem is same, this tree. We want to reach at this M, huh? We want to reach at this M. The goal is M. We will start from A. The goal is M. And the limit is what? 2. 2 means this level, huh? This is 0th level, this is 1th level, and this is 2th level, huh? Limit means this 2. So goal is after it. So we will not reach at the goal. One thing is sure, huh? One thing is sure that we will not reach at the goal. But how that algorithm will execute, let's see that. So this limit will go. So initial state of the problem is what? It is A, and then problem, and then limit is 2. So I am first I can write this thing. Just a minute. Now this is not possible on the screen. I should have to move on the whiteboard for a better understanding of this algorithm. Oh no. The other way is I can open a MS Word file and there I can write, huh? That is the better solution. If that is what only for recording. Well, I am putting too much force to clean it. Coming back to MS Word file, huh? Okay. What other options I have here? If I will do that, I will not. I can write here, but then you will not see anything, huh? I can write notes here, but I am saying that then you will not be able to see anything. Okay. Can I move this to some portion else? Is it visible now?
Yes.
I will write the values here, okay? But now I cannot use the pen, huh? Okay. So now my first call is DLS, problem and limit, huh? So I'm writing capitals DLS, okay, whatever is problem and limit may be 2, huh? Now I can, let's see, where is, yes. So now my first call is the problem. Problem is what? Problem is, you can say this is the state space. Initial state is A. We want to reach at M. And the limit is what? 2. And the limit is what? 2, which means this level. And goal is after it. So one thing is sure that we will not reach here. Okay, now, so the first call is DLS and the problem information and the limit. So then what? Where is my word file? Here I am writing DLS problem and the limit is what? 2. I am calling it. And then, okay, then we are calling recursive DLS with the initial state of the problem. Okay, problem information and the limit is 2. So recursive DLS, we are calling, after it, we are calling recursive DLS and then initial state is what? A. We are leaving this problem, okay? We don't need that. That is understood, huh? So, and then A the initial state and the limit is what? 2. We are calling this recursive DLS. And this is now recursive DLS. So initial state, that is A and the limit is what? 2. It can return solution failure or cutoff. I explained what is cutoff. Cutoff is the boundary, huh? So now here we are checking that this A is a goal. We are checking this A is a goal. No, it is not a goal. So then this condition is false. We will go next. And here we are checking else if limit is equal to 0. We are checking limit is equal to 0. No, the limit is not 0. It is what? It is 2. So then condition is false and then we will move here on this last else portion. And all these statements are under it. So then first, what is happening here? Cutoff occurred false. So the value of cutoff occurred is what? False. Okay, we are keeping it in memory that the cutoff is false. And then we have this loop for each actions on that node. What is that node? Node is A. And how many actions are available on that node A? According to the tree, 2 actions, B and C are available. Okay, B and C are available. Okay, so this loop will execute how many times? 2 times for B and C. So it will take first the first children. So now that children is B. And here we have another call to this recursive DLS. We have another call with this child B, the problem information, and limit is 2. 2 minus 1 is 1. So B and 1, we are again calling. And when we are calling, I am writing it here. So recursive DLS with, and I am writing it with a tab so that you will understand that this is first call was A and 2, and then we have another call in it, huh? And we are calling B and 1. Okay. When we are calling, then we will go there again. And what is the node now? Node is now B. And what is the value now? Value is 1. And then we are checking B is goal, no. Limit is 0, no. Then else. Cutoff occurred, false. Cutoff occurred is still false in the previous call, and I can write here, okay, if in the previous call, okay, I can just write cut is what? Cut is false, huh? And here, oh, so when we called it first with A and 2, cutoff was false. A and 2. And when we called it second for B and 2, so the cutoff is again false. And here we are checking how many actions are available. How many actions are available on the node B? Again 2. Again 2. What are those? This D and this E. These two actions are available. Okay. So this loop will execute now 2 times. One for D, one for E. So now we are taking the first child, which is what? D, recursive DLS, and we are calling it with D, and limit is what? 1 minus 1, 0. So D and 0. Okay. So it is another call. It is another call under B, recursive DLS, D and 0. Another call. So when you are calling again, you are going here. Node is what? Now node is what? Node is D. And the limit is what? 0. Okay. So this node is goal? No. Limit is 0? Yes. Then return what? Return cutoff. Returned cutoff. This is some string value, you can say. So now the call with the, now this call which was with the D and 0, and when you executed, it is returning what? It is returning cutoff. So it is returning what? So this is giving us what? Cutoff. This call RDLS D0 returning what? Cutoff. Okay, when it is returning, it means this statement is now complete. This execution is now complete, huh? It is returning what? It is returning us cutoff. So that cutoff will be stored here in this result variable. And then what? We are checking. If result is equal to cutoff, yes, condition true. Then cutoff occurred, true. Then we are changing the value of the cutoff occurred previously, which was false. We are changing it to true. And when we are calling this D, this was the execution of the previous step. Are you understanding? Initially, that's why I have written here. So this call is returning me what? It is returning me cutoff. And previously this was in execution. This was the call. And here the value of the cutoff was false. Now that value is what? Cutoff. So if result is equal to cutoff, then we are changing the value of the variable which was previously false. We are making it true. And this was the execution of what? The for loop execute 2 times D and E. D and E. So this loop while executing for D, okay, this is previously it was executing. Maybe I will give you. Are you understanding what I want to say? If I will draw a tree, then maybe you will understand. The tree is already there. We can have idea from here. This is the first call. This is the first call to recursive DLS. And the loop is executing 2 times. Then this is the second call to the recursive DLS. This is the first call to recursive DLS. This is the second call to recursive DLS. And then loop is executing 2 times. And here, this is the third call to recursive DLS according to this document. This is the first call, this is the second, and this is the third, which you are seeing here. This is the first call, this is second, and this is third. And third is returning you the value cutoff, which will go to the previous call. Okay, this is what I want to say, because this program is recursive. This program is recursive. So now, so here, if result is equal to cutoff, yes, it is cutoff, because what is the value in the result? Cutoff. Then cutoff occurred true. Then you are changing the value of this variable, which is true. Else if will not execute. This will not execute because it is connected with this if. And now these are the statements under this for loop. This if is not with this for. This if is not with this for. I am now erasing all that stuff. These 4 conditions are with this for. This if is not. So cutoff occurred true. So we changed the, so cutoff occurred true. Okay. So here we were at this call is now finished. This was the call of this B, and B has 2 children, D and E. Loop is executing for D and the E. D is finished. What is then remaining? Now, this loop is executing for what? D and E according to the tree. D is finished because it is returning us cutoff, and we have done all that thing. What is remaining? E is remaining. Are you understanding? I am making a mixture due to this recording, okay? If it would be on the whiteboard, it would be very much easy, okay? But just bear this time only for maybe 1 or 2 lectures more, than maybe for the next lecture, maybe I have the recording already. I will mix them up. I don't know, but let's see. So now D, this loop for D is finished. E is remaining. So now, so after this, we will go again to this loop. D is remaining. This D is finished. E is remaining. So this loop will execute for E. And here the child is what? E. And we are calling again DLS with limit. What is the value of the limit? Yes, this is what initially at A, initially it was 2. I can give you the understanding from here. Initially it was 2. When we called this B, it was 1. When we called this D, it was 0. And now for E, what is the, for example, when we are executing now, so now when this loop is executing, here we have child E, recursive DLS. Child is what? E. Now what is limit? The value of the limit is 1, and then 1 minus 1 is 0, okay? Because here, if you see, this is the value. This 1 minus 1, it is becoming 0 here. And then when you will execute it for E, then 1 minus 1, it will become 0 here. These are the two childrens under this B. Anyhow, I made this algorithm complex, otherwise it is not, okay? So now, so that limit, previously limit, the value of the limit is 1. So 1 minus 1, now it is 0. And the child is what? E. Child is what? E. So we are calling the RDLS with E comma 0. So we are calling for this now. We are calling this DLS again. With node E, limit is now what? 0. We are checking E is a goal node? No. Limit is 0? Yes. Return cutoff. Cutoff occurred. Again cutoff occurred. Because why it is occurring? Because this is the limit that you have set for the algorithm. That algorithm should not have to go beyond this boundary, beyond this limit. So anyhow, so cutoff occurred. When cutoff occurred, so this was the call, and now you executed, and it is returning what? It is returning cutoff. That will go into this result variable. And then you are checking result is equal to cutoff. Yes. Then change the value of cutoff occurred with true. So now what is? So now this RDLS, which we are calling, this will return what? It will return cutoff. And now it is finished. I changed the color. So these two were the children of B. This was the previous call. Anyhow, so, and this B was the children of A. A has two children, B and D. B and D. So now this loop is finished for two children, D and E. Now this loop is what? Finished for two children, D and E, which are the children of B. Okay. This else if will not execute because if as is executed. So when this loop is finished, I will come here at this if. At this if, I will come here. And here I am checking cutoff occurred. Here you change the value of cutoff, which is now true, huh? Here you are checking. Here you are checking. Here you are. So now this for loop is finished for B and D. But which loop is executing previously? This is the question. This is the question. Previous loop, this loop is still in execution. So for D and E, it is finished. It is returning cutoff. It is returning cutoff. And this, so then what? This was the call to B. So it means B has now some value. But the other children for A is still remaining. I am stopping here for recording because I cannot see your sad faces. And I am going directly to the whiteboard for a better understanding. These are the class. Even Pakistan is better than this thing, okay? Pakistan does not have the resources. Okay? Why we are here? Because we are suffering there. Even then again, I'm saying Pakistan is much better than this situation. We don't have the whiteboards like here. We have fixed whiteboards on the wall, huh? Which you can use for the screens, even for writing. No extra boards.
So for example, this is, I'm just drawing a tree. I have further nodes, but I'm not drawing. Because in this example, I will go up to only this level. Huh? Now, the algorithm is in front of us. We are calling first DLS with the limit what? With the limit 2. With limit 2. And then we are calling recursive DLS, second line. Recursive DLS, recursive, I am writing it recursive LS. Recursive LS with the initial node A and the limit. Limit is what? 2, the same. Now, I am moving here. So this was the call. So this was the call. So the control will go here with node A and the limit 2. And now I am executing. I am now checking that my node A is a goal. No. Limit is 0. No, because limit is what? 2. So then else cutoff occurred false. Cutoff occurred false. And here, so here, okay, you can say just for that we are executing, and here we are writing, okay, leave it. Maybe where I have write in a better place. So we are executing. We will keep it cut off. Okay. CF is equal to F. F means false. So cutoff occurred false, and then we have a for loop. Then we have a for loop. For this node, node is A. How many actions are available on this node A? 2 actions, B and C. So this loop will execute 2 times. Only then you can come out of this, otherwise not. So then what? Okay, first we are taking node is A, we are taking the child of that node A, and we will keeping it. What is that child? What is the first child of this node A? B. So we are taking that B here in this child. And then we are calling recursive DLS with this B. Leave this problem. Problem means problem information. And limit is what? Limit is 2. 2 minus 1 is 1. So B and 1, you are calling this recursive DLS again. So I will go. So you are calling. I am just drawing the tree again for your better understanding. So we are calling recursive LS again. It is not complete yet. It is incomplete, huh? It is still in process, huh? So we called again recursive LS with B, and the limit is what? 1. Go again. And then this node B is a goal? No. Limit is 1? No, we have 1 limit, not 0, huh? Yes. So then we will come here. Cutoff occurred false. Okay, I am writing here. Cutoff is what? CF is equal to F. And then I have a for loop again. This for loop for it is incomplete. One is executed, other one is remaining. Why I am drawing this tree? I am drawing this tree to represent the for loop. Okay. I said for this RLS, loop will execute 2 times. 1 time is over, but 1 is remaining. And now I am here. Child is what? B. How many actions are available for the B in the tree? Again, 2. D and E. So this loop will execute 2 times for 2 children. And then, okay, child is, I am taking the first child of the B. What is the child of the node? At node B, what is the child? D. So now the child is D, calling again with D, and limit is what? 1 minus 1, 0. So again calling. It is still incomplete, huh? I am writing incomplete. Okay. It is still incomplete. And I am calling again RLS with D and 0. We will go again. We will go again with the values, and here we are checking node D is goal. No. Limit is 0. Yes. Limit is 0, then return cutoff. And here we are returning what? Yeah, simply we are returning cutoff. Okay. When it is returning cutoff, this is giving result to the previous call. Anyhow, because this call was executing previously. This call was. It is not complete yet. Other loop is remaining. This call B was halfly executed. So when cutoff occurred, it will give the result here. Cutoff, okay, in the result I have the cutoff. Result is equal to cutoff? Yes. Then cutoff, the value of the cutoff occurred, this variable is now true. This variable is now true. So this is giving us some value true, huh? So which will go there? Which will go there to the previous one. Okay. So else it will not execute. So the first time, so in the previous call, one call is finished, other is remaining. So one loop is finished, other is remaining. So I will go again to this for loop. And what is the other action for the B? Here. And so I will go again for the second. So the node, here the node is B. So for this node B, what are actions are available? D and E. D is finished, E is remaining. So now this loop will execute for the E child. So in the child, I have E and I will call recursive DLS. Child is E. Limit is what? Again 0 at the same level because the value is 1. 1 minus 1 is 0. So here, RLS, child is E. Maybe you are not seeing it. Okay. And 1 minus 1, 0. So we are calling recursive DLS again. So calling again, what I have written? E. So E, node E is goal test? No. Limit is 0? Yes. Return cutoff. So here I will have, it will return cutoff. And then what? When it will return cutoff, it will come here. Result is cutoff, then return cutoff true. So now this is returning cutoff true. So which is again going here. Now this was incomplete, but now it is complete. The previous call for the B is now complete. So when I was executing, but this B is the call for the A. So it means that the loop for the A, which will execute 2 times, 1 time for A is finished. 1 time for A is finished. The other thing is remaining. And here the limit is what? 2. That is the only difference, huh? Here the limit was 1, we were considering. But now the remaining loop for the A, 1 children of A is finished. One child of A is finished. or one loop of the A is finished. Loop for the other child of A is remaining. I said it is incomplete. You can see it is incomplete. So this is completed, but it is incomplete. So that loop still I have to execute. So here A. So now okay, if I have to do that, so now here we are cutoff is true, huh? What we are getting here when the loop is finished, or you can say when we called A loop was going on, and then recursive DLS for B was recursive DLS for the child B was executed, and it is giving us what? Something in the result. Something in the result. Cutoff occurred true. Okay. And we are checking. That now I have value what? I have this value in the cutoff variable. Okay. So this one and this one. So now B is finished. It is also returning some value here. It is also returning some value to the previous RLS. And what is that value? Let's see that. It is still incomplete. So if I say result is equal to true, this is false, I will come here. Result is not equal to failure. Yes, not equal to failure. That is returning result. That is not. So 2 loops for B is finished. For B, 2 loops are finished. When these 2 loops are finished, we are executing B. Okay, then cutoff occurred, then return cutoff. We are going out. I don't want to go out first. Okay. And then now we are moving towards the other part. One loop is finished for the A, other loop is remaining. I said one loop is finished and the other loop is remaining. Okay, what is the other child for the A in the tree? That one, C. Okay, then C. What is the other child? C. In the child, I have C. Recursive DLS. Child is C. Limit is what? 2 minus 1. 2 minus 1, which is incomplete. 2 minus 1 is 1. So we are calling again recursive DLS with the value child is what? C. And the value is 1. And the value is 1. Okay. Now we are calling again with this with this C. Okay, C is a goal test. No. Limit is 0. No. Else. Cutoff occurred. False. So here cutoff is what? False. Here cutoff is false. And how many actions available for the C? In the tree, F and G, 2 actions. F and G, 2 actions. So this loop will execute again 2 times. Okay. And then I am getting on the C node, what is the children? I will get F. So now in the child I have F and I am calling it again. So now recursive LS with F and the limit is what? Previously it is 1. 1 minus 1 is what? 0. It is still incomplete. Okay. I have, because it is still in process. Huh? So this incomplete and complete I am writing for the loops. Okay. So RLS F0. So I am calling again this RLS with F and 0. Go again. F is a goal. No. Limit is 0. Yes, 0. When limit is 0, return cutoff. So then it is giving me the cutoff. It is giving me the cutoff. Where I was? Here. When it is giving me cutoff, I am again checking. Cutoff occurred. Then cutoff is what? True. So it is returning the value true now. this true value I will consider here, but still one loop is remaining, huh? One loop is remaining. Okay, because I have evaluated this statement. So loop is finished. Then I will go again to this loop. And what is the next child from the node? What child next I will get? G. Child is G, and the limit is what? 2 minus 1 is, oh sorry, 1 minus 1 is 0. So I will call again this what is RLS with the G, and limit is what? 1 minus 1, 0. So call again. So we are calling this again. We are checking that this is a goal, this is not a goal. Limit is 0, yes, return cutoff. Cutoff occurred when we are returning cutoff. Then in the previous call, here, huh? In the previous call, you are calling RLSG. Okay, call. When you are calling RLSG, what was the previous call? Previous call was this. Okay. Previous call was this. And here, the G is returning result. That result you are evaluating here in the previous call. Huh? So anyhow, result cutoff occurred, return that cutoff true. So you are returning cutoff true from here. From here you are returning true. From here you are returning true. Previously it was incomplete and you have the true here. Huh? And previously it was, now it is complete and you have the true here. Hmm? And similarly, you here, so this was the call to them and they are returning something true here, huh? Something true here. And when you, so now, when you call this for A, huh? When you now imagine, when the node is A, limit is 2 or something, we are checking, okay, this is not goal, limit is not 0 else, and you are coming here. So when everything is finished, so first child, second child, when everything is finished, you come here. Huh? Now everything is executed here. And now you will come here in the last statement. And then you are checking if cutoff occurred. What is the value of cutoff occurred? True. So if true, then return what? Cutoff. Here we are returning that you reached on the cutoff and you didn't find any solution, huh? So if cutoff is true, then we are returning boundary cutoff. And if cutoff is false, then we are returning what? Failure. And if we will have some solution, that solution will be, we are returning here within these loops. When you reach on the solution, so this was the worst condition. This was the worst condition which I executed, okay? If solution is there, for example, if B is the solution, huh? And then you know that this loop will execute for the B somewhere, huh? And if your child is B something, and here child B with some value, you will come here, and then you are checking B is a goal, yes, then return that node. Okay, solution returned. That would be an easy case for me to give you the understanding. But this cutoff is the worst condition, okay? Worst condition, which is checking all the nodes in the tree. And here, for example, this true, and here you are checking cutoff is true, then return cutoff. No, you are on the boundary, but you have nothing in your hand. Okay. Understood or not? Understood or not, I don't know, but I'm sure that now this gives you a better understanding as compared to this recording that we were going on with, huh? Okay. I don't know what I have, where we were reached here. Okay.
So now we have seen already this on the whiteboard, but just for a quick look. First we are calling it with the limit 2, and here the node was A and the limit was 2 in the first call, and then we were checking something like that, and then here we executed this loop for we will execute this loop for B and C according to the tree. For B, this loop is now done and we are checking, and then here we are calling this recursive DLS. We are calling this recursive DLS. What are the children of this B? What are these? D and E, huh? D and E. For D, this call is done. And the limit for the D is what? Here the limit is 2. And when we called this again for the B, the limit was 1, I think. And here the limit is 0. I'm executing many steps in my mind, okay? So and here, when you called it for E, the limit was 0. No, it is not goal. Your goal is maybe M, which is not available in the tree, huh? So then these calls, it is returning somewhat, it is returning true in the cutoff, okay? And now C will be executed. C will be executed, and then it will be executed for what? F and the G. Here the limit would be 0. First it will execute for F, then it will execute for G. Here the limit would be 1, huh? And then it will return what? It will return again cutoff, and the cutoff value for the cutoff would be true. And this was the call to this thing with this A. So that cutoff will be true here again. And finally, when all these steps are executed, then you will check that this cutoff is true, the value, because you are getting the value of cutoff is true here. When cutoff is true, then return cutoff and not failure. And if this cutoff is false, then you will return failure. But here we are saying cutoff is true, so which means we are returning that the algorithm has reached on the cutoff, not on the solution. So for recording purpose, it is not good. Otherwise, it is good. So anyhow, leave it. What I will do. Okay. So now, then what is happening? So now depth limited is finished, and now we have iterative deepening DFS. The disadvantage of this depth limited search is that if our goal is not, for example, if our goal is available after this cutoff, after this limit, then DLS is not going to find the solution, huh? This is the drawback. This is the drawback of this depth limited search. That if your solution is after the limit, then you are not going to find the solution. So then what? To remove this drawback, we have another idea. To increase the depth, to increase the limit one by one until you find the solution. Okay? So the idea of, for example, if my goal is this M, so first I will execute the depth limited search, this previous algorithm. I will execute this with the limit 0. And when limit is 0, you are checking only the root node. And then your algorithm is checking, is it a goal node? No. Then it will do what? It will increase the limit to 1. Now your depth is up to the next level. But you will execute the depth uh, first search again from the root node. So you will start again from the root. You will add the further 2 nodes in the frontier. You will check on the left, it is a goal, no. Then you will check on the right, it is a goal, no. Because this is the limit, so your algorithm will not go beyond it. But it is executing like DFS because the tree is small, huh? Now, so you didn't find any solution, then you algorithm will do what? It will increase the limit to 2. And then it will execute the things again, starting from root node. A, it will expand these, it will go to the left in the deeper side. This is goal, no. It will expand the depth further, and then it will check. So now you have 2 nodes, D and E here. It will go on the left on the deeper side. This D is a goal, no. Then this E is a goal, no. Then according to the depth first, it will come to this C, huh? And then it will come to this C, it will expand, and then it will check F is a goal, no. Then it will check G is a goal, no. Then what? If it is not finding, then in the next step, it will increase the limit to 3. And then it will start again. So with this approach, definitely our algorithm will find the solution, huh? With this approach, because in each step we are increasing the limit. So for example, when the limit is 3, okay, we are starting again with this A. We are adding 2 next nodes in the frontier, and from the left we are checking that it is a goal, no. Then we are expanding this B according to the depth first search, and we are adding further 2 nodes in the frontier, and we are selecting on the left, checking it is a goal, no. Then we are adding further 2 nodes in the frontier, and on the left we are checking it is a goal, no. This is the last point of the state space, huh? So then what? We will check this I in the next step. It is a goal, no. According to the DFS. And then what? We will go back and we will see this R. Expansion is possible, so we will expand it first. And then we will check on the left, J is goal node, no. And then we will check on the K node, no. Goal node, no. And then we will go behind according to the DFS. We will check the C. Expansion is possible, so we will expand first. Introduce some new nodes in the frontier, and then we will check from the left. We will select F. Further expansion is possible. L and M. Here we are checking L is node, no. M is node, yes. Then algorithm is going out of the algorithm is taking exit from its structure, huh? Because it is a goal node. So here, this idea is called iterative deepening DFS. And here we are increasing limit on each step until we find the solution. So now this algorithm will definitely give us the solution. And it is removing the drawback of the simple DFS. Let's see what is the algorithm for that. So now this is the function. The name is iterative deepening. We are passing problem into it. It will return solution or failure. And here we have a simple loop. Depth is 0 to infinity. This depth means limit, okay? This depth means that limit variable. And it is starting from 0 to infinity. So it means it will remain continuous until it finds the solution in the state space. If the solution is there in any depth. So for depth 0 to infinity, then we have these 2 statements under this for loop. The first is we are calling depth limited search, this previous algorithm that we have seen. We are calling this. So we are calling this DFS here. And we are passing problem and the depth, whatever the depth is. Initially, the depth is 0. And when depth is 0, it will execute like that. It will execute like that. If your goal is M, then the initial step will execute like that. And now, when it will be finished, it will return something. So initially, when limit is 0, actually cutoff occurred actually. Cutoff occurred. So then what? It will return something here in the result variable. And here we are checking result not equal to cutoff. But actually result equal to cutoff. In the first step. So then what? Condition false. Condition false. So this will not execute. And you will come back here to this for loop. And now the depth will be 1. Depth will be what? 1. And you are calling this depth limited search again with depth what? With depth 1 now. When the depth is 1, now it will be executed like this. That algorithm will execute like this. A and then B, C, checking that B is goal, C is goal, no. Then cutoff occurred, So here cutoff occurred. When cutoff occurred, this function will return cutoff in the result. And here we are checking result not equal to cutoff. No, it is cutoff. It is cutoff. Then condition is false. So it means this will not execute and you will again go to there. And here the depth is now 2. And if the depth is 2, this algorithm will execute like this. And if your goal is M, it will execute the DFS. It will not find your goal and the cutoff occurred. And then what? Again, cutoff occurred, matching, nothing will happen. You will go again there. Now the depth would be 3. And it will execute the things like that. And here, the goal is M, for example. Then cutoff is not occurring. Okay? Then cutoff is not occurring because you are reaching at the goal. And then what? This function will return something in this variable result. And here you are checking result not equal to cutoff. Yes, not equal to cutoff because you have the goal. Then return that result. If that result is goal or what, that will be returned. Okay. So this is how this iterative deepening DFS is executing. And then we have a bi-directional search. Bi means 2 directions. Direction. So 2 directional. So idea here is, if you have some tree, you will start from the root node and you will also start from the goal node. Okay. For any problem, normally you have the initial node and the goal node. So, and then you have the state space. You have the tree in any direction. So your algorithm will start from the root node and it will go in any direction. It will go in any direction in the state space. And the search will start from the goal node back towards the initial node. Back towards the initial node in any direction. And then we will combine these 2 searches at some point common, at some common point. Then these 2 searches will what? They will meet with each other at some common branch of this tree. And in this way, you will find the solution from the root node to the goal node in half time. Because 2 searches are executing parallel. Now you have multi-processors in your machines. One processor will do that, other processor will do that in parallel. And this algorithm will run fast. This is the only difference. You can execute breadth first search over here. That would be easy. You can imagine starting from start node root node and breadth first search like that. So you can imagine that here goal node, this is starting node, and then breadth first search level 1, level 2, level 3, and here from the goal node in backward direction level 1, level 2, level 3, and somehow this search will meet with each other, and then you have the solution. So here normally, if you will use BFS, breadth first search, then the breadth first search has the time complexity B raised power D. But this search will give you not D is the depth of the solution. Now it would be divided by 2, half. Half. B divided by 2 and B divided by 2. One for this, one for this. And if you will calculate final time complexity of this, you will ignore one term, and then the big O of this algorithm would be B D over 2. Yes, this would be the big O for this algorithm. So the time complexity is reduced to half. This is the comparison which you already know. For each algorithm, we already have seen these things. For the BFS, if I will go back to the BFS, here we said BFS is complete if finite, optimal if step cost identical. Time complexity is this, space complexity is this. Similarly, for UCS, we have discussed these 4 things. Similarly, for DFS, we discussed these 4 things. And depth limited search we didn't discuss, but it is the same. Now this table is giving you again all these 4 things for all the algorithms. Just a comparative table. So BFS is complete, yes, but there is a condition on A. And what is that A? It is mentioned here. Complete if B is finite. Okay, this is the meaning of that A. Order of BD time, we already seen. Order of BD. And optimal, BFS is optimal? Yes, but there is a condition. What is that? C. C is what? It is mentioned here. Optimal if step costs are identical. We already have seen. Identical means same. Similarly, uniform cost search. Complete? Yes, with 2 conditions. A is what? A is finite states. A means if the finite state space, and B means complete if step costs are greater than or equal to epsilon. Epsilon is what? Positive value, greater than 0. We already have seen in the algorithm. And this is the time complexity, this is the space complexity we already saw when we were studying that. Optimal, yes. Depth first search, we already have seen this. Depth limited search, let's see that. Because this is not mentioned there. So complete. Depth limited is complete? No. Because know that if solution is after the limit, we will not find that. So it is not complete. Optimal? No, it is not optimal. If it is not complete, definitely it would be not optimal. Then time and space would be what? Order of B raised power L. L for limit, okay? Because maximum nodes, worst case, L for limit, B raised power L. Limit. It would be like that, okay? And here it would be order of B multiplied with L. Here B multiplied with M, maximum depth. Here is maximum depth is up to the limit, not more than that. Not more than that. And then iterative deepening, complete? Yes, iterative deepening is complete with the condition. What is that condition? Complete if the state space is finite. Okay, no repeated states. Iterative deepening, that is optimal. Yes, it is optimal with this condition C. What is C? Optimal when step costs are same. Okay, not different values, step cost. Time, okay, BD, because iterative deepening will go up to the solution. It will find the solution. And if the solution is there, then you can mention it with D. D is the depth of the least cost solution. So here it is becoming power. Here we are multiplying. Bidirectional, the last one that you here, this one, huh? You can read it in the book. In the book, it is theoretically available. Okay, you can read it by yourself. You can apply the breadth first search over it. Okay, so this is again BFS. Okay, this is again BFS, not a new algorithm. Not a new algorithm. You have to apply the BFS from the start, and also you have to apply the BFS from the node in the backward direction. So bidirectional, it is complete. Yes, it is complete. It is optimal. Yes, it is optimal. It is complete with two conditions, A and D. A is what? With the finite state space. But what is D? D means if both directions will use BFS. So this algorithm will be complete if you will apply BFS. Okay, this is also a condition. This is our breadth first search. And now here, it is optimal with these two conditions C and D. C is what? Optimal when step costs are identical, same. 1 1 1 1 1 1 1 1 1, huh? Or no step cost. And what is D? Both directions use BFS. Where it is. And then space complexity, we already know D by 2, D by 2. So that is just a comparison. And then we will start heuristic search strategies, which is the other part of this CO. This blind is finished. The other one is heuristic. We will start this in the next lecture, huh? But again, okay. I want to execute this again for recording purpose, but leave it. Okay. Hmm. Your name is? Isa. Isa.